Here's another problem involving floor functions. In this problem, we are asked to find the general form of non-negative integers which cannot be expressed as the floor of 2x, 3x, and 6x. We can work out a few examples. For example, if x is an integer, let's say x equals 1, we get the floor of 2 plus floor of 3 plus floor of 6, and that's 11. If we try, let's say, x equals 1.5, we get 2 times 1.5 plus 3 times 1.5 plus the floor of 6 times 1.5. We get here 3, 4.5, and 9. The floor of 3 is of course 3, the floor of 4.5 is 4, the floor of 9 is of course 9. So the sum of this one is 16. So we can work out a few more examples, but as you can see here, by jumping by 0.5, coming from 1 to 1.5, we effectively skip a few numbers. Coming from 11, we got 16. And if we try maybe, let's say, 1.2, let's try 1.2. We get the floor of 2 times 1.2 plus the floor of 2 times, 3 times 1.2 plus the floor of 6 times 1.2. We have here 2.4, 3.6, and 7.8. Get the floor of that, we get 2, 3, and 7. If we add them, we get 12. So, from 11, we got 12 by jumping from 1 to 1.2. And then if we see the next one, it's 1.5, we get 16. Let's try to get, let's say, 13. Let's try 1.3. 2 times 1.3 plus 3 times 1.3 plus 6 times 1.3. This is 2.6, 3.9, and 7.8. Get the floor of that, we get 2, 3, and 7. It's the same as the previous one, so we still get 12. So we haven't got 13 yet. So we've tried 1.2, 1.3, and 1.5. How about 1.4? Let's try 1.4. 2 times 1.4 plus 3 times 1.4 plus 6 times 1.4. We get here 2.8, 4.2, and what's this? 8.4. Get the floor of that, 2, 4, and 8. Add them, we get 14. Unfortunately, we are not able to get 13. So we got the 11 if we tried 1. And if we tried 1.2, we get 12. 1.3, we get 12 again. We try 1.4, we get 13. And at 1.5, at 16. So it seems from here that really some values cannot be expressed in terms of this sum here. And that's the goal of this problem. We are trying to generalize and state which of the positive integers cannot be expressed in this form. So this is just first part that I just want to show a motivation for the solution. So for the next part, we'll discuss how to properly solve this problem. To solve this one, we would write x as k plus, let's say, m over 6, where k is a non-negative integer, so that's a natural number. Sorry, whole number. So that's a whole number, and m is m is from 0 to 6. 1, 2, 3, 4, 5, 6. Actually, we don't need 6 because if it's 6, this will just be 1, and we can put it as part of k as another integer. So this is our m. And why exactly are we writing this fractional part here as m over 6? Why can't we write it as just, let's say, f as the fractional part? Because m over 6 is still a fraction if you consider this values here for m. But we do this specifically to create a division between the values that would make different values for the floors of this 3 here. Specifically, we choose a denominator of 6 because that's the least common multiple of 2, 3, and 6. And so we expand this by substituting k to each of the floors. So we get here the floor of 2 times k plus m over 6 plus the floor of 3 times k plus m over 6 plus the floor of 6 times k plus m over 6. I'll just distribute the coefficients for each of them. We get 2k plus m over 3 plus 3k plus m over 2 plus 6k plus m. Now, since k is an integer as we've previously assumed, actually it's a whole number as we assumed, we can take this out of the floor to leave us with 2k plus floor of m over 3 plus 3k plus the floor of m over 2 plus 6k plus the floor of m. But we know that m is actually a whole number as well. So this here can be written as simply as m. Now we have a couple of variables here, or common terms with a coefficient of k, or a variable k. So we can add them up to get 11k plus m plus the floor of m over 3 plus the floor of m over 2. From here, we'll just do a bashing of cases for the values of m that we've set. So let's say the column here is for the value of m. So that's 0, 1, 2, 3, 4, and 5. And here we have m. Then here is m over 3, and then m over 2. For m here, we'll just copy these values. This is just the value of m. For m over 3, anything below 3 would give a floor lower equal to 0, because that's the value of m over 3 is less than 1. So 0 over 3, floor of that is 0, 0, 0. And if we get 3, 3 over 3 is 1, so the floor of that is 1. 4 over 3 is 1.333, so the floor is also 1. This is 1 as well. For m over 2, if it's less than 2, the floor is 0. If it's 2 onwards, it's at least 1. For example, at m equals 2, 2 over 2 is 1, so the floor is 1. 3 over 2 is 1.5, so the floor is 1. 4 over 2 is 2, the floor is 2. 5 over 2 is 2.5, so the floor is 2. Finally, we add them to get this expression here. Oops. To get the expression that we want. So add them 0, 1, 3, 5, 7, and 8. Therefore, this thing here is actually 11k plus, let's say, y, where y is an element of 0, 1, 3, 5, 7, and 8. Therefore, the only integers that can be expressed in terms of this expression here is in the form 11k plus y, where y is part of this set. Therefore, the answer we're looking for are values that will give values outside of this set. So 11k plus y, where y is element of 2, 4, 6, and 9. In other words, the integers that cannot, the positive integers that cannot be written in the form this is or are the integers whose remainder is 2, 4, 6, or 9 when divided by 11. And that's our final answer. So I think the biggest part or main highlight of this solution is representing x in this manner. The crucial part here is determining when or what values of m will result to certain integers or certain values of x. As an exercise, I'd like you to try to find the integers that can be written in the form 2x plus 3x plus 5x plus 6x. So there's an addition of 5x compared to what we did earlier. The method is the same, and it should work regardless of the number of items here. I hope you learned something from this video, and if you haven't subscribed yet, please consider doing so. Thank you for watching and have a nice day.